Hi, this is section 2.6 called Relay Rates. It's a very powerful section. We're measuring the rates of change of different amounts that are related to each other. For example, if you're filling up, the rate of change of the depth of the water is related to the rate of change of the volume of the pool. So if we're trying to find the rate of change of the depth of the water, we would use the derivative of the depth of the water to represent the rate of change of the height of the water, or the depth of the water. And that's related to the rate of change derivative of the volume of the pool. Notation, dv dt and dh dt, because these are both going to be elements based on time. We're going to have to remember dv dt. So derivative change of volume based on time, dv dt. If we're talking about an airplane that's flying, the rate of change of its horizontal distance from the starting point. So here's my airplane up here. Here's where it started. This distance is different than this distance. So this is my horizontal distance. That's different than the rate of change, but it's related to the rate of change of this direct distance here. So this distance, s, is actually the distance from here to here, and this distance, x, is the distance from here to here. But the rate of change of that distance would be this, and the rate of change of that distance would be that. So those rates are related. As the plane flies, these two rates are related to each other because it moves. All right. If we're talking about free fall, like the man who just jumped out of the airplane from the longest free fall time, the rate of change of his height as he falls is related to the rate of change of the angle of elevation from the camera on the ground. So all of these rates are derivatives, and they are related to each other. So let's review how to take the derivative with respect to time, because we're going to have variables, different variables that are going to be related to time. So suppose x and so that means that y is a function with t in it and x is a function of t in it. So both of these variables are probably related to each other with time. So when we want to take the derivative, we're trying to find dy dt. Take the derivative of y, which is 1 dy dt. Take the derivative of x squared, that's 2x, and then dx dt. So we're taking the derivative with respect to time. It's different than the variable here, so we can't just take the derivative like normal. We have to also multiply by the derivative of x. Plus, and then the derivative of 3, any constant is always going to be 0. So now we have taken the derivative. We've got these different variables, dy dt, we've got x, and dx dt. Now we plug in the things that they've given us. We're trying to find dy dt when x equals 1. So after we've taken the derivative, we plug 1 in for x. Given that dx dt equals 2, so then we can plug 2 in there. So the rate of change of x based on time is 2 when x equals 1. So we can't plug in any of these numbers until after we've taken the derivative. And now we have taken the derivative, so we can plug in our numbers. So we have 2 times 1 times 2. So dy dt, the rate of change of y with respect to time is 4. And we'll usually have units on that. This is just a stripped down, bare basic example, just to review how to take the derivative with respect to time. Here's guidelines for solving related rate problems. The first and most important step is to identify all the given quantities and the quantities that you're supposed to find and label them. So that's dv dt or dr dt or whatever quantities we're trying to find. The rate of change of r, you're going to use dr dt, etc. Identify all the given quantities and the quantities to be determined, so what you're trying to find, and make sure you label them. Okay? Then we're going to write an equation involving the variables. It might be an equation with volume or circumference or volume of something that you don't know the formula for volume of. How can you find volumes and circumferences and distances if you don't know the formulas? Well, they're somewhere in your book, possibly. If they're not, you can always Google them. You've got this great tool. So if you need the volume of the formula volume of a cone, don't get stuck, just look it up. Find it on the internet, use it. Use the things that you have at your disposal. All right. Then we're going to use the chain rule to differentiate with respect to t implicitly. And then after step 3, after we take the derivative, then we substitute in the values. Okay? So let's use that. A pebble is dropped into a pond. Ripples form concentric circles. So we've dropped our pebble in, and then there's ripples. They're concentric circles, much better than mine, okay? The radius of the outer circle So the distance from the center out is increasing at a rate of 1 feet per second, 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? All these words, we've got to reduce down into some variables, okay? The radius of the outer circle is increasing at a rate. So the rate of the radius. Rate is always derivative. We want the derivative of the radius. So dr dt. You've got to be able to translate the rate of something into this notation. And that equals 1 foot per second. When the radius is 4 feet, so r equals 4 feet. For later, that's when that happens, okay? At what rate, so this is what we're trying to find, at what rate is the total area of the disturbed water changing? So we want the rate of change of the area. So let's use A for area, and rate of the area, the rate of change of the area is dA dt. That's what we're trying to find. So we've labeled all of the things that they've given us, these two, and what we're trying to find. So now we need a formula that has an R in it and an A in it. Anyone know a formula that's based on a circle that might have an area and a radius? Okay, if you don't know it, you can look it up. But the area of a circle is pi r squared. So you're going to have to find some formula based on the situation. So we know we're working with a circle, radius, and area. So use that. Okay, then we take the derivative implicitly. Derivative of A with respect to time is dA dt. Remember, pi is just a constant, so it could be like 7. Take that r, that power on the r, and multiply it out there. So it's 2 times pi. And then decrease the power by 1, so 2 minus 1 is 1. Also, times the derivative of r with respect to t. We're taking the derivative with respect to t, and t is different than r, so we have to multiply by this. Another clue is we had this given to us. If we forgot the dr dt, where would we have put that? Okay, you'd luck out on this one because it's just 1, so multiplying by 1 doesn't change anything. But what if this were 2? Then you'd have the total wrong answer because you forgot to multiply by this. So let this notation also be a reminder about your implicit differentiation. Now that we've taken the derivative, we can plug in the value they've given us. So we're going to plug that in there, we're going to plug that in there. Don't plug anything in until after you've taken the derivative. So our answer is 8 pi. And what would the units be? For area, based on feet, it's square feet per second, because it's a rate of change. It's per time, based on time, and our time is measured in seconds. You can analyze the units. R was 4 feet. dr dt was 1 foot per second. Feet times feet is feet squared, and it's divided by seconds, so per second. So you can use a unit analysis to figure out your units, or just think logically about it. dA dt, so the units for area are going to be square feet, and the units for time go on the bottom. All right, let's do another example. The radius of a sphere is increasing at a rate of 2 inches per minute. So just stop right there. Radius of a sphere increasing at a rate of 2 inches per minute. We're going to write dr dt. It's the rate of change of the radius. It's 2 inches per minute. If it were decreasing at 2 inches per minute, we would write -2. So remember, if it's a decreasing amount, use a negative for your rate. But we find the rate of change of volume. So we're trying to find the rate of change of volume. Volume rate of change is dV dt. That's what we're trying to find. They give us r equals 6. And another one, r equals 24. So we've got 2 answers to find. All right? What kind of object are we talking about? Because we need some kind of formula that relates radius and volume of a sphere. So I need the formula for volume of the... So we've got all of our variables identified. The thing that we're trying to find is identified as a variable. And we've got an equation that relates all of our variables. The next step is to take the derivative with respect to time. So dV dt equals 4/3 pi is a constant. So that's going to cancel. And then subtract 1 from the exponent. And also remember to multiply by the derivative of that inside function there, the radius, because it's based on time, not r. Now we can plug in values. dv dt equals 4 pi. R is 6 inches, and it's squared. And then dr dt is 2 inches per minute. So we've got 6 squared, which is 36, times 4. And the units, square inches times another inch, is cubic inches. Does that make sense? If we're trying to find volume, the rate of change of volume would be cubic inches, and it's based on time, so per minute. 288 cubic inches per minute. And then we're going to do the same thing, but with the 24. So use that dv dt we had, and this time plug in 24 for the radius, and still 2 inches per minute. And that's 4,608 pi cubic inches per minute. Sorry, forgot to do B. Explain why dv dt is not constant, even though dr dt is. Okay, so the rate of change of the radius is constant. It will always stay 2 inches per minute in this example. But notice the rate of change of volume is different based on the radius. Why is that? Well, dv dt is proportional to r squared. It's got an r squared in it. So if r changes, then our volume is going to change. The volume will be changing the rate of change of the volume changes based on what r is. dr dt might be constant, but r is changing. So then our rate of change of volume will also be changing. If our rate of change of volume didn't have an r in it, if it were some kind of thing like this where it just had a dr dt in it, then the volume would also be constant because dr dt is constant, and all we're doing is multiplying it by 3. But the volume, rate of change of volume, has a variable in it other than this constant variable here. So that's why our volume rate is changing, even though dr dt is not. Okay, find the rate of change in the elevation of this rocket ship. Rate of change of the elevation of the camera. So the camera is watching the rocket ship as it goes up. So we're trying to find the rate of change of this. We'll call it theta at 10 seconds after liftoff. So find rate of change. So we're trying to find some kind of rate of change. So it's something with respect to t. The rate of change in the elevation. So we've chosen that theta is the angle of elevation. S is the position. And this is 2,000 feet. So S is the height of the rocket ship. All right? So we're trying to find the rate of change in the elevation of the camera at 10 seconds after liftoff. So time equals 10 seconds. So what are our variables? We've got S is the height of the rocket. We've got theta is the angle of elevation. T is time. And we need an equation that relates S and theta. Well, we've got a right triangle. Could we use Pythagorean's theorem, like a squared plus b squared equals c squared? No, because I don't care about this, and it didn't involve the angle. I need an equation that involves the angle and the height. So how about some trig? We've got opposite and hypotenuse. So what equation would relate the opposite side and the hypotenuse? Or, I don't know anything about the height really, so let's maybe use this one. The rate of change, or an equation that involves this 2,000 and the hypotenuse, or the opposite side. 'Cause I don't really care about this at all, so I don't really care about the hypotenuse. So I need some equation that involves this and the thing I know. So the angle, the opposite, and the adjacent. So opposite over adjacent would be tangent. So let's use that equation. Tangent of the angle equals opposite over adjacent. So now I've got an equation that relates all my variables that I care about, and I want to take the derivative of that. So the derivative of tangent is secant squared theta times the derivative of theta. And then this is like 1/20th times S, okay? So S is the function, and 1/20th is just a constant out in front. So when I take